Okay, let's get started today. If anyone is having any problem with the audio, please type in a question in your question box. But let me say hello to you all and welcome to our webinar, Concrete Temperature Monitoring with Data Loggers. My name is Cynthia Selby and I'm on the Marketing Communications team here at Onset. I will give you a very brief introduction and then I'll turn over the presentation to our speakers today from Hoskin Scientific and from Davrock and Associates. First, I'd like to share a little bit about Onset for those of you who don't know us. We are the company that makes the industry-leading HOBO data loggers used all over the world for building performance monitoring, environmental research, and water monitoring. We've been making data loggers since 1981, and we've sold a lot of them, over 2 million so far. We have 120 employees located here in Massachusetts on beautiful Cape Cod, where we design and assemble all of our products. And we have a global network of dealers that serve our customers around the world. The webinar will run for 1 hour today, and we'll save time for questions at the end. So please type them into the questions section on your go-to control panel at any time. We are recording the webinar, and I'll be sending you a follow-up email within a few days. There'll be a link to the recording, and you'll be able to view it at your convenience. And finally, please take a minute to complete the short evaluation, which will pop up after you close out of the webinar. Now I'd like to introduce you to Joseph Zambito-Orazio, who is Manager of Materials at Hoskin Scientific in Canada. Joseph earned his civil engineering degree from the University of Toronto, and he began his career working at a consulting firm and later moved on to an engineering products manufacturer. For over 14 years, he has been with Hoskin Scientific, recommending and supplying testing equipment to meet the modern challenges of quality control and quality assurance. We also have with us today Sal Fazzulo of Davrock and Associates, and he's got over 40 years of experience in the field of concrete technology, and has been managing and serving on board of directors for a testing lab as well as on the board of directors for the American Concrete Institute. And Sandeep Makar of Davrock is also with us, and he has a number of years' experience in the field of soils, asphalt, and concrete, and serves as a project manager in Davrock testing labs. So I'd like to welcome all of you and thank you for sharing your time and expertise with us today. And Joseph, let's start with you.
Thank you for the introduction, Cynthia. Can you hear me okay?
Yes, I can hear you fine.
Okay. Good afternoon, everyone. I would like to thank all the registrants for taking some time to attend in this presentation. In this webinar, we will briefly discuss various aspects of curing concrete. The various topics we will touch upon include: what is concrete curing and how does it occur? What can happen if concrete is not cured properly? What aspects affect the quality of curing? We will discuss temperature in particular. And what can you do to control the curing process? Okay, so let's begin. Curing is a hardening of cement over time. The American Concrete Institute recommends a minimum curing period which allows the concrete to reach 70% of the specified strength. This can take 3 weeks or longer. There are various factors that affect the curing time. These can include the mixture proportions used, the specified design strength, the size and shape of the concrete member, the type of cement used, for example, ASTM C150, type 1, 2, 3, or 4, and any admixtures which were possibly included. As cement mixes with water, a chemical reaction known as hydration occurs during the heat, during which heat is generated. When this process occurs, heat gets trapped and cannot escape quickly. As such, the core of the concrete structure continues to heat while the surface cools. This can lead to large temperature differentials developing between the core and the surface of the concrete structure. In the bottom right corner, you'll see some images showing some percentages of reactive cement compared to unreactive cement. These temperature differentials can lead to thermal cracks. Once this occurs, the concrete becomes susceptible to increased permeability from water and air, which can reduce the durability, structural integrity, and ultimately the life of the structure. There are a number of control strategies that can be implemented for minimizing cracks depending on the project type. For instance, one can ensure that an appropriate mix design has been selected. You can use insulation, chemical spraying, or steam to control the temperature. Also keep in mind that post-cooling strategies should also be considered for a given length of time. The Porcelain Cement Association stipulates three main functions of curing. Firstly, you want to maintain the mixing water in the concrete during the early hardening process. Secondly, is to reduce the loss of mixing water from the surface of the concrete. And lastly, you want to accelerate the strength gain using heat and additional moisture. Sorry, Cynthia, I'm trying to go to the next screen now. Oh, there we go. Sorry about that. Let's look in more detail at what the impact of curing temperature has on concrete. The effects of temperature early in the life of concrete can strongly influence long-term stability. In general, concrete temperature peaks at 48 hours and remains constant for 7 days. The larger the concrete structure, the more heat it will generate on its own. Managing the heat of hydration becomes more challenging when dealing with mass concrete. The industry uses a general rule of thumb to define what size constitutes mass concrete, as any placement of concrete with a minimum dimension greater or equal to 36 inches. This dimension will vary based on the jurisdiction. The differential temperature, air temperature, and concrete mix temperature are all important factors to consider. In general, concrete temperature should be maintained above 50 degrees Fahrenheit or 10 degrees C to achieve adequate strength. Uniform temperatures also need to be maintained. This can be very challenging with cold and hot weather extremes. Cold weather can prevent proper hydration if the temperature is at the freezing point or drops below zero. Hot weather can speed up the curing process and lead to short-term strength gain. However, excessive heat ultimately leads to weaker concrete. Issues can arise with high concrete curing temperatures. There can be an increased water demand due to evaporation or the combination of high winds and low humidity. There is an increased chance of shrinkage cracking as the top layer dries faster than the lower layers. Higher curing temperatures can produce an early strength gain, but can potentially decrease the 28-day strength. And there is an increased potential for reinforcement corrosion due to the moisture and air entering through the cracks. Issues can arise with cold concrete curing temperatures as well. Since water freezes in concrete capillaries at 28 Fahrenheit or -2 C, this can lead to improper curing and low strength gain. This is because the ice formation prevents the cement matrix from fully developing. There can be up to a 50% compressive strength reduction if the concrete freezes before reaching at least 500 psi or 3.4 MPa. Ice occupies approximately 9% more volume than water. The forces generated by the expansion of ice is what makes it detrimental to the long-term integrity of the concrete during the early curing stages. In order to help prevent the potential for these adverse curing conditions, we must know and understand the batching temperature, the temperature the concrete is producing during hydration, and the environment it is curing in. Temperature monitoring is critical to ensure the long-term strength and stability of concrete structures. It is necessary to verify that the temperature differentials do not go beyond the specified design limits and that the concrete does not cool by more than 5 degrees Fahrenheit or 2.8 Celsius per hour during the first 24 hours. You also need to verify that the temperature consistency was maintained during the curing process. Knowing what the core temperatures are at during the various curing stages is imperative to determine what control strategies need to be put in place, like heating blankets, insulation, or hot steam. Knowing the temperature profile can also be used to determine wind forms and support structures can be removed so the next construction phase can begin. Industry associations such as American Concrete Institute, Portland Cement Association, and ASTM, as well as government institutes, provide some guidance with the temperature specifications of concrete. For instance, concrete which is placed and cured at 95 Fahrenheit or 35 degrees C or higher will have lower long-term strength than concrete cured at room temperature. The Precast Concrete Institute specifies a maximum cure temperature of 180 degrees Fahrenheit or 82 degrees C. Some states also have requirements on maximum temperature differentials during the curing process. For instance, the Florida DOT specifies a maximum temperature differential of 35 Fahrenheit or 19.5 C between interior and exterior portions of concrete structures. There can also be contract-specific requirements based on local practices and site conditions. Thermocouple data loggers provide a cost-effective, simple way to take in-situ measurements in concrete as it cures. They provide users with around-the-clock measurements and reporting of temperatures at critical locations. These data loggers accept a wide range of thermocouple probes and can be configured and installed in minutes, making them extremely versatile and user-friendly. The LCD display readout allows viewing of current live temperatures and indicates if high or low threshold alarms have been exceeded. This is convenient for spot checking your concrete conditions during the curing process. There are also different models to choose from which allow for a single or multiple thermocouple inputs. Having models with various input channels is convenient when designing and implementing your monitoring project. Depending on the specified monitoring location and quantity, you can choose a variety of combinations to suit your budget and still comply with the design specifications. Questions to consider include how many points need to be monitored and what locations need to be monitored. Are your monitoring points located very close or far apart? Let's look at what some common monitoring practices are in industry today. Typically, temperature sampling rates are selected from every 10 minutes to once per hour. In cold weather curing conditions, users usually select a faster sampling rate to monitor changes more closely. The monitoring period usually lasts several days but can vary based on design specifications. For multi-channel logger applications, thermocouple sensors are often placed at the bottom, middle, and top of the concrete structure. An additional channel for ambient air temperature is also included in the onset thermocouple data loggers. This combined information allows the end user to determine if temperature gradients have exceeded their contract specification. If so, corrective measures can be taken. A weatherproof enclosure is also a must to protect your data loggers from the elements. For more detailed information concerning the various items in this webinar, please feel free to view the following articles. ACI 301, specifications for structural concrete, ASTM C31, standard practice for making and curing concrete specimens in the field, a Wikipedia article on concrete and curing, the ACI Concrete Center knowledge, as well as math concrete heat from the Portland Cement Association. Thank you for your attention. Next, we have a presentation from a consulting firm who applied the use of thermocouple data loggers to record the concrete curing temperatures of a high-profile construction project in Toronto. Dabrock & Associates Limited is a Canadian-owned firm of consulting engineers, technologists, and specialists providing a full range of services in connection with the construction, maintenance, and rehabilitation of buildings and structures. Dabrock provides personalized consulting engineering services to help their clients achieve practical, responsible, and sustainable engineering solutions within time and budget constraints. I'd like to introduce Sandeep Makar, who is a Senior Project Manager, and Sal Pasulo, Vice President of Dabrock & Associates.
Good afternoon. My name is Sandeep, and I'm here with Sal Pasulo. Together, we'll be presenting concrete temperature monitoring. It's a case study with on-set data loggers at number 1 York Street, Toronto. The purpose of the concrete temperature monitoring was to ensure that the concrete slab temperature does not go below 10 degrees and to ensure top, middle, and bottom of the slab temperature does not differentiate more than 10 degrees Celsius. Even though it was month of September, our client wanted us to make sure the concrete does not freeze or before set. And the last reason for concrete monitoring was to monitor the thermal stress between the concrete. The thickness of the concrete slab was approximately 2 meters, 6 feet. And 4 concrete pumps were used to pour this concrete. And the thermocouple, sensors were installed 1 day before the concrete pour. And the Type T wire thermocouple sensor was installed in the concrete pour area. On-set data loggers were used to collect the temperature data. And the data loggers were stored on site in a wooden box and a plastic bag around it to protect it from the rain and any construction activities. And this on-set shuttle was used to transport the data from the site to the computer, so it could transfer every day, go to the site and take the data from the hobos and put it in the computer. Here's another shot of the wooden box where thermocouples were stored. And the data loggers were placed right next to the formwork. We drilled some hole in the formwork and brought the wires out. And the temperature monitoring was carried out for 10 days. And the readings were taken every hour. Here's what it looks like when we took a screenshot of the HoboWare software when we brought the readings into the computer. And this is the data once we got it from the thermocouples. We input that into the Microsoft Excel. And you can see the blue is ambient, which is at the bottom. And white, green, and red is the top, middle, and bottom of the slab. That's where they were installed, top of the slab, middle of the slab, bottom of the slab. And you can see the data, it peaked at the 60 degrees approximately. and it was 35 MPa concrete. And all three, like top, middle, and bottom, is like kind of like following the pattern almost, all the way through. And now this graph is showing from the side face of the concrete pour slab, where you can see some difference in temperature readings in top, middle, and bottom, because it was the side face of the slab. And temperature monitoring was carried out by Deborah. If you have any questions, go ahead. Thank you.
Okay, let's take a look at some questions that we've received. Has everybody had an opportunity to send in questions? Now would be a good time. Just go to the chat screen, or rather, I'm sorry, to the question screen on your control panel and send them in to us. I'm going to read a few questions, and I believe that I can select the person that should be answering, so let me do the best here that I can. As a precast manufacturer, let's see, do we need to monitor our concrete with hobos, especially when the concrete poured is generally 150 millimeter in thickness? Perhaps Sandeep, you could address that question?
It's Sal. I'll address that question.
Okay.
I mean, the concern in the precast industry is a number of reasons. Number one is, when can they release the panel from the forms? And in other cases, it could be, when can they release the pre-stressing strands that are in the concrete? So strength is a concern, and strength is related to how much time, how much temperature that concrete is given. So the hobos in the precast settings, we use to monitor the maturity of that concrete. And we pre-establish the maturity versus compressive strength curves for that concrete. So this is another way that we use the hobos in a precast setting.
Okay. Let's see, we've also been asked if you have strength data that corresponds to the mat pour temperature data.
That's right. Because every mix, there'd be a face mix or a standard backup mix in a precast environment. They all have their own unique maturity versus strength curves.
Okay. Again, there are several more questions, and I'm not sure, Sal, if you can see some of the questions, but they're very specific to your expertise. Can you explain why in the cold weather, when calcium is added to the mix, the concrete weeps water for weeks afterward? Is that something you may know or be able to address?
Say that again. The concrete does what?
Can you explain why in the cold weather, when calcium is added to the mix, the concrete weeps water for weeks afterward?
No, I can't. It needs to be looked at a little bit more detail as to what the mix was, what the gradation of the aggregates were. There's a number of unknowns.
Okay. Let's see. On slide number 15, which I think might be yours, Joseph, showing 3 locations of thermocouples, would you not recommend to place one near the edge, close to the 2 surfaces? Is that?
Sal, maybe you can jump in on that from your past experience of consulting with precasters.
Yeah, from our past experience, on jobs that we've been on, what we typically try to do, number one, we picked different locations. So yes, we are concerned about the side face of the forms because obviously that has formwork on it. Sometimes those forms are insulated. Sometimes they're made of steel, which transfer heat losses from the concrete. So we need to know what those temperature differentials are on the side face. On the top face, typically to maintain the block of concrete a uniform temperature, we most often will insulate the top surface of the forms so that we don't have a great differential between the ambient temperature, top surface of the concrete, and as you proceed into the depth of the concrete. So definitely we do multiple point testing, and where we have critical temperatures that we want to know, we double up on the thermocouple sensors. And the reason for that is sometimes we lose the odd sensor in the concrete, so that's another reason why we double up on those locations. So we have two confirming hobos at, say, the center or the bottom or the top side face, and it's good confirming information for us. It does not take a huge amount of additional time to add the additional hobo sensor.
And they never touch the concrete surface. Is that right?
The hobos?
Yeah. The sensors, yeah.
The sensors we will also place directly on the surface of the concrete underneath tarping to sense the top surface of the concrete. We will typically place the top hobos at the rebar level, and sometimes we will place them directly on the surface underneath any protection, which is typically insulating blankets.
Okay. I'm not sure if you said this already, but do you leave the probes in after the test?
Oh, the probes are left in typically for between a 7 to 10 day period. And the reason for this is typically concrete will peak somewhere between 36 hours to 48 hours, depending on the concrete mix. And then we also want to monitor the concrete in the cool down period until we virtually cool down to ambient temperature almost.
Okay.
So that typically takes about 7 to 10 days, depending on the time of year we place that concrete.
And we leave the sensors in the concrete after.
Yes.
And you leave them in there.
It'd
be pretty hard to get them out, I'd imagine.
Yeah, yeah.
They're embedded in the concrete. We just leave them there.
All right. Let's see if we have another question or two for you. If data is analyzed daily, does this give enough time to make real-time adjustments to the curing process before it's too late?
Yes, yes. Typically, once we have the data, we're either adding protection or removing protection to control the differential. The important thing with all these jobs is that we discuss concrete mix design and how to minimize the temperature rise in the concrete. And that's done through the use of supplementary cementing materials, larger size aggregate where we can, specifying instead of 28 days specified strengths, sometimes 56 day, sometimes even 91 day strengths. Why? Because let's face it, that slab doesn't need full strength 28 days until months down the road when it's time for loads to be applied.
Mm.
So we use all these techniques at our fingertips to minimize temperature rise in the concrete.
I see. Now another question here is how difficult is it to install the thermocouples? Do several of them fail because of abuse during concrete placement?
Well, the reason why sometimes things fail is because concrete is dropped. You can imagine the slab is 6 feet or 2 meters in thickness. Concrete is dropped sometimes a great distance. Vibrators may damage or break the wire. What we do in the installation process is the wires themselves, the ends of the wires are tied to reinforcing bars. They're protected with electrical tape. All of the wiring is typically run underneath at the bottom surface of the rebar, so it's not exposed to any vibrators entering the concrete or anyone stepping on them. You definitely don't want to put your thermocouple wire on the top of rebar, because let's face it, people will step on it, vibrators will hit them. So, and either tape or tie wire is used to fasten the thermocouple wire to the reinforcing bar cage.
Okay. Let's see. So yes, that answered some of this question. How do you mount the sensor? And what type of thermocouple do you recommend for concrete curing? In other words, type K or any other type?
We've been using the type T wire for the temperature ranges that we are looking at.
Okay. And let's see, how frequently do you look at the data? Do you look at it daily? I believe you may have addressed that.
Yes.
Okay. And do recommended temperature profiles vary if fiber reinforcement, such as fiber mesh, is added to the mixture?
Typically not. There shouldn't be a reason why adding fiber mesh should affect the temperature. I mean, we're looking at the same mix. Now, because of the addition of the fibers, if the mix slump has been increased for workability, then obviously the temperature rise of that mix might be affected slightly. But adding fibers should not affect temperature rise.
Okay. And let's see, your typical logging intervals, what would those be?
A typical logging interval is 1 hour. Sometimes we'll stretch it to 2 hours. We try to make the data manageable. Like in 1 hour intervals, we usually don't see large increases or reduction in temperature. So we vary it between 1 to 2 hours, sometimes even 4 hours.
Okay. And let's see, are you willing to take another question or two? All right. Does adding or removing insulation blankets affect the core temperature significantly?
Adding or removing insulation in the core, it doesn't significantly affect the core, but it will start to affect the surface temperature.
Okay. And let's see, another one about precast concrete panels are most of the time installed within 72 hours of casting. If we were to leave the thermocouples in for 10 days, what good would this do to the panel after it has been installed, especially if the temperature were found to be too low, perhaps? I believe that's too, yes.
In a precast environment, the main point there is they need to recycle those forms on a daily basis. So the purpose of the temperature monitoring there is really to give them that data within that 12 to 15 hour window when they're looking to either cut the stressing strands, to release them, or to remove the form, to remove the panel from the formwork. So that's the main purpose of monitoring temperature in the precast environment. If we're looking to see whether the panels are being cured properly after they've been demolded or the stressing strands have been cut, that's a matter of just simply monitoring the environment where those panels are being stored.
All right. Now, what was the total cost of the temperature monitoring implementation on this particular project? Can you estimate approximately what you would have spent on loggers and thermocouples and?
Yeah, you know, as a very ballpark figure, because, you know, we vary job to job in the requirements.
Mm-hmm.
So the installation, the thermocouples, the hobos themselves, the daily visits for monitoring temperature, they were basically in the order of $6,000 for this particular mass slab. And keeping in mind here now that we just didn't put one set of thermocouples. We had multiple sets of thermocouple wire in various locations in the slab.
Okay.
1,000 foot of wire.
Let's see. Does adding, and again, I don't know what this means, but I'll ask you, Sal, does adding EPS beads affect the temperature of the concrete, lightweight concrete? Not sure what that means.
I think it depends on the mix, you know. I mean, I can't see if the beads would be for what purpose? Replacing air, entrained air?
Polystyrene beads,
yeah.
I guess they are, yeah.
Polystyrene beads. So if it's, I'm assuming this is perhaps a lightweight concrete. So the polystyrene beads are used to reduce the weight of this concrete. So either you reduce the weight with polystyrene beads or with foaming the concrete. So if you assume that the matrix is the same with or without the polystyrene beads, I can't see that there would be a substantial difference in the temperature properties of the concrete. The polystyrene beads may act more as an insulation, thereby retaining the heat longer.
Okay.
And perhaps maybe even resulting in a higher overall temperature.
All right. Let's take one or two more questions if you're willing, Sal. These are all directed to you. On a large project, how do you determine how many locations to monitor? Do you monitor each pour or multiple disparate locations along the pour? For example, a retaining wall or slab, how many areas would you recommend measuring?
Yeah, generally speaking, if we're talking about slab concrete, and if we're talking about you know, slabs that are even as thin as 8 inches, 200 millimeters, or even as thick as 2 meters, 6 foot. Again, we do like to position our thermocouples in areas of concern, exposure to wind, sun. So take, for example, we try to at least get 2 to 3 side-face locations, and we try to get at least 2 or 3 internal slab locations. As far as wall concrete goes, again, we're looking at how long is the wall, how thick is the wall, how many meters would make up that wall, and then we would decide. Again, we never do just one set of thermocouple locations at one specific spot in the wall. And the reason for that is we want to see what's happening throughout the length of the wall. So maybe for a, take for example, a 100-foot wall, we may want to do at least a minimum of 3 locations, 3 to 5 locations along the length of that wall. And again, we would do the front face rebar, the back face rebar, and at least one in the middle of the concrete. And we would vary that at the bottom, middle height, and top of that wall.
Okay. Excellent.
And depending on the time of the year, we may even increase the number again. Why? Because in the wintertime, we're worried about whether we've got good protection along the length of the wall, make sure that there aren't any openings in the curing protection or the heating protection that's being provided. Whereas in the summertime, we may reduce the number.
Okay. Let's see. One person is asking if we have software that graphs the data, or does the user have to map the data in Excel? And of course, yes, we do have HoboWare software for graphing the data. You certainly can export to Excel as needed, but we do have HoboWare, which is part of the Onset product suite. And let's see, I think we've pretty much covered most questions.
Cynthia, I'd like to add something about the wire being used. Typically, the most popular ones we've supplied are type J, K, and T. T has a more narrow range, and it gives better accuracy. And there's different types of T you can use. There's the actual thermocouple wire, extension grade wire, and then we get into what's called a special grade limits wire, which brings the accuracy even tighter. So depending on the project specifications and the total accuracy they need to achieve, that's where we decide, which type of wire to supply with the Hobo loggers.
Okay, perfect. I'd like to just say before, in fact, let me put up our next slide, which is some contact information. And I want to thank everyone, and in particular our panelists here for presenting today and sharing your expertise. And I want to be sure that you're aware that Onset has application specialists that are available online, calling 1-800-LOGGERS to help answer questions, any questions that you may have, and certainly help walk you through some of our products that are suited for this concrete temperature monitoring. So please be sure to give them a call. And also Hoskin Scientific, located in Ontario. I've posted a phone number and website address for Hoskin, and certainly for Sal and Sandeep as well. This is their company website. So be sure and contact our sales team or our application specialists, or certainly Hoskin if you're up in Canada. And I really appreciate everyone's attendance today, and thank you so much for joining us. And again, thank you to our panelists for your wonderful expertise. And have a great afternoon, everyone.
Thank you. All right, thank you.
Thank you.
Thank you.